So your interviewer just asked you, what's the time complexity of your solution? Don't worry, I got you. I'm Tara, I'm a senior software engineer, and I used to teach computer science at Carnegie Mellon. This is my intro to time complexity and big O notation. Time complexity quantifies the amount of time an algorithm takes to run as a function of the length or size of its input. Think about it as, how does my runtime change as the size of my input changes? What happens when I double my input size? How does the runtime change? Does it also double? Does it quadruple? And I'm going to teach this through two different functions. The first function is find value, where basically we're given an array, like 1, 2, 3, 4, 5, and we're looking for a value, maybe 78 randomly. We'll return the index of where we find this value in the array. If it's present, we'll return -1 if not. How much work do I need to do in the worst case? Well, the worst case is actually right here. It's if the value is 78. It's not in the list at all, right? That means we had to look at every single element in our array before returning. And so this loop, in the worst case scenario, ran n times. That means that this function is O of n. So this function is called pair sum. We return the indices of two values that sum to a target value. So let's actually visualize what this work looks like. So on the first pass, I'm looking at like 1, and I'm comparing 1 to 2, 3, 4, and 5. So it's kind of like 2, 3, 4, and 5. And I'm making all those comparisons to see if they equal my target value. On the second pass, I start with 2, and then I'm looking at 3, 4, and 5. On my third pass, I'm looking at 3, and then I look at 4 and 5. On my fourth pass, I'm looking at 4, and I'm looking at just 5. This kind of looks like a pyramid or a triangle, right? If you look at all of this work that we're doing, how many total pairs do we need to look at? Does anyone know the formula for this? I think it's something like, it's like n times n plus 1, and then this whole thing divided by 2. When we talk about big O, we want to talk about the most dominant term in this function, because really we're concerned with the asymptotic behavior of these functions. So what happens when the input is really, really big? And so whenever we have really, really big numbers like that, the constants and the lower order terms don't matter. And so if I actually do a little math right here and I factor this out, we get something that's like, let's see if I can even do this, n squared plus n on the top, right? That's the numerator. And then we would divide that by 2. But 2 is just a constant, so we actually just ignore the 2 entirely. So we kind of have this little polynomial right here. And then again, we focus on the highest order term and the most dominant term, so we just ignore this n right there. So the big O of this function is n squared.